High in the Peruvian Andes, overlooking the ancient city of Cusco, stands a fortress wall that survived 500 years of devastating earthquakes that have reduced Spanish colonial buildings to rubble. These aren't ordinary walls. They're constructed from individual stones weighing up to 200 tons, cut into bizarre, irregular polygonal shapes that interlock like a three-dimensional jigsaw puzzle with no mortar holding them together. The fit is so precise that you cannot insert a knife blade between the stones. When earthquakes strike, these massive blocks actually dance, shifting slightly during the tremors and then settling back into their exact original positions without collapsing. This is Sacsayhuamán, and it represents Incan engineering at its absolute peak. Spanish conquistadors who first saw these walls believed they were built by demons or giants because humans with simple tools couldn't possibly achieve such precision. Modern engineers examining the site agree on one thing. We still don't fully understand how the Incas did this. No mortar, no wheels, no written language, no iron tools. Yet they created earthquake-proof architecture that has outlasted everything built by the technologically superior Spanish who conquered them. Sacsayhuamán sits on a hillside overlooking Cusco, the capital of the Incan Empire, at an elevation of over 12,000 feet. The name in Quechua, the language of the Incas, roughly translates to satisfied falcon or speckled head, though Spanish chroniclers corrupted it to Sacsayhuamán and various other spellings. The site covers a massive area, with the main fortification walls running in zigzag patterns for over 1,000 feet, creating defensive bastions that could house thousands of warriors and protect the sacred city below. When Spanish conquistadors led by Francisco Pizarro arrived in Cusco in 1533, they were astounded by Sacsayhuamán. These were men who had seen the great cathedrals and fortifications of Europe, yet they struggled to comprehend what they were looking at. One Spanish chronicler, Pedro Sancho, wrote that the fortress was built from stone so large that no one who saw them would say they were placed there by human hands. Another, Garcilaso de la Vega, who was himself part Spanish and part Incan nobility, described the construction as the work of enchantment, made by demons rather than men. The largest stones in the walls weigh approximately 200 tons, though some estimates go higher. To put that in perspective, that's roughly the weight of a fully loaded Boeing 757 aircraft. These massive limestone and diorite blocks were quarried from sites miles away, transported to the construction site at 12,000 feet elevation, shaped into complex polygonal forms, and fitted together with tolerances measured in fractions of an inch. And this was accomplished by people who had no knowledge of the wheel, no draft animals larger than llamas, which can't pull heavy loads, and whose hardest tools were made of bronze, a metal softer than the stone they were shaping. The construction technique is what truly baffles engineers. Unlike Egyptian pyramids with their regular rectangular blocks or Roman walls with standardized stone sizes, Sacsayhuamán features stones of wildly different shapes and sizes fitted together in 3 dimensions. Each stone has a unique irregular shape with multiple flat faces meeting at various angles. The adjacent stones are carved to match these faces exactly, creating interlocking joints that are visible but imperceptibly tight. This isn't random. This is deliberate engineering genius. The irregular polygonal style actually makes the walls more stable and earthquake-resistant than walls built from regular rectangular blocks. When an earthquake strikes, rectangular blocks can shift and slide against each other in predictable planes. But irregular polygonal stones interlock in 3 dimensions, meaning they can only move if multiple stones move simultaneously in coordinated ways, which is far less likely. The stones essentially grip each other mechanically through their complex shapes. The precision of the fit serves multiple purposes. First, it distributes loads more evenly across contact surfaces, reducing stress concentrations that could cause cracking. Second, it eliminates gaps where water could penetrate, freeze, and cause expansion damage. Third, it creates friction that helps hold the wall together without mortar. The weight of the stones, combined with the friction from the tight fit, creates a structure that's stable under its own mass and remarkably resistant to seismic activity. Cusco sits in an active seismic region. Major earthquakes have struck repeatedly over the centuries, including devastating quakes in 1550, 1650, and 1950. Each time, Spanish colonial buildings constructed with mortar and regular masonry collapsed or were severely damaged. Churches, palaces, and administrative buildings had to be rebuilt multiple times. Yet the Incan walls, including those at Sacsayhuamán, survived these earthquakes largely intact. Modern Cusco is filled with buildings that have Incan stone walls on the ground floor topped with Spanish colonial construction, and invariably the Incan portions survive while the Spanish portions require reconstruction. So how did the Incas achieve this? The honest answer is we don't know for certain, but archaeological research and experimental archaeology have provided plausible theories. The process likely began with quarrying. The Incas identified suitable stone outcroppings and used a technique called thermal fracturing by building fires against a rock face to heat it, then rapidly cooling specific areas with water. They could create stress fractures that allowed them to break off large chunks of stone. Bronze chisels and harder stone hammers were then used to rough shape the blocks. Transportation was a monumental challenge. Without wheels or suitable draft animals, the Incas relied on human labor, ropes, wooden rollers, and sledges. Moving a 200-ton stone would require hundreds or possibly thousands of workers pulling in coordinated effort. Experimental archaeology has shown this is possible, but incredibly difficult, especially in mountainous terrain. The Incas may have used earthen ramps, lubricated paths, and incremental progress measured in feet per day rather than miles per day. The real mystery is the final fitting. Here's where theories diverge and speculation increases. One theory suggests the Incas carved template stones at the quarry, rough-fitted them there, numbered or marked them somehow to maintain positioning, then transported them to the construction site for final placement. This would minimize the amount of heavy stone that needed to be moved back and forth for fitting trials. Another theory proposes that stones were brought to the site rough-shaped, then final carving was done in place using a technique of careful scribing and grinding. The builders would position a stone approximately, mark where it contacted adjacent stones, remove it, grind away the high spots, reposition it, and repeat this process until achieving a perfect fit. This method is labor-intensive but proven to work in experimental reconstructions. A more controversial theory suggests the Incas had some method of softening stone temporarily, perhaps using plant extracts or chemical processes unknown to us, allowing them to shape and fit stones more easily before the stone hardened again. Proponents point to strange scoop marks and apparent molding characteristics on some stones. However, mainstream archaeology dismisses this theory as lacking evidence, and no known chemical process could soften igneous rock like diorite and then have it re-hardened to its original hardness. What we do know is that the Incas were master stonemasons who developed their techniques over generations. They didn't suddenly achieve this capability. It evolved through centuries of construction projects across their empire. Earlier Incan sites show progressively developing masonry skills, from rougher work to increasingly refined techniques culminating in the spectacular precision of Sacsayhuamán and other late-period construction. The organizational capacity required was enormous. The Incan Empire had a system called MITA, a form of labor tax where citizens owed the state a certain amount of work time. For major construction projects, the Inca could mobilize thousands of workers from across the empire. These weren't slaves, but citizens fulfilling their obligation to the state. They were fed, housed, and cared for during their service. Spanish chroniclers recorded that 20,000 workers were involved in Sacsayhuamán's construction, working in rotating shifts over many decades. The chronology of Sacsayhuamán's construction is debated. Traditional history attributes the major construction to the reign of Pachacuti, the ninth Sapa Inca, who ruled from 1438 to 1471 and dramatically expanded the Incan Empire. However, some researchers suggest construction began earlier and continued through several reigns, possibly spanning nearly a century. The sheer volume of stonework supports a lengthy construction period. The fortress served multiple purposes beyond defense. It was a ceremonial center where important religious festivals were held. It housed storage facilities, administrative buildings, and quarters for the nobility and garrison. The site included sophisticated water management systems with channels and cisterns. This was a multifunctional complex, not merely a military installation. The Spanish partially demolished Sacsayhuamán after conquest. They removed stones to build churches and colonial buildings in Cusco, particularly the cathedral. This destruction focused on the upper portions of the walls and the buildings that once stood behind the defensive walls. What remains today represents perhaps 40% of the original complex. Despite this, what survives is still impressive enough to astound visitors and challenge engineers. Modern preservation efforts face challenges. Tourism brings revenue, but also wear. Thousands of visitors walk on and touch the ancient stones daily, gradually eroding surfaces. Acid rain, pollution, and climate change accelerate weathering. The Peruvian government and UNESCO work to balance access with preservation, implementing measures to protect the most vulnerable areas while allowing people to experience this remarkable site. Recent archaeological work has revealed more about the site's extent and complexity. Ground-penetrating radar and excavations have found buried structures, additional walls, and tunnel systems that suggest Sacsayhuamán was even larger and more sophisticated than the visible ruins indicate. Some tunnels may have connected different parts of the complex or provided secret passages for defenders during sieges. The earthquake resistance continues to impress structural engineers. After the 1950 earthquake that damaged much of Cusco, engineers studied the Incan walls to understand their seismic performance. They found that the combination of massive weight, tight-fitting, interlocking shapes, and slight inward lean created structures that could flex during seismic events without failing. Modern earthquake engineering has adopted some of these principles, particularly the value of flexibility over rigid strength. There's a poetic irony in Sacsayhuamán's survival. The Spanish, with their advanced metallurgy, written language, mathematical knowledge, and European architectural traditions, couldn't build structures that matched the earthquake resistance of the walls created by people they considered primitive. The Incas, without written engineering manuals or formal mathematics as Europeans understood it, achieved structural performance through empirical observation, incremental refinement, and accumulated practical knowledge passed down through generations of master builders. This points to different types of knowledge and intelligence. The Incas didn't have a theoretical framework of European science, but they had deep practical understanding developed through trial and error over centuries. They knew what worked because they'd tested it, refined it, and proven it through actual construction. Their knowledge was embedded in practice rather than written in books, but it was no less sophisticated or effective. Modern attempts to replicate Incan stonework have met with limited success. Using period-appropriate tools and methods, researchers have managed to create small sections of fitted stone wall, but achieving the scale and precision of Sacsayhuamán remains beyond casual reproduction. This doesn't mean it was impossible for the Incas. It means we haven't fully recovered their specific techniques, their tool handling skills, their quality control methods, or their accumulated generational knowledge. Standing before the walls of Sacsayhuamán today, running your hands over stones that weigh more than most houses, tracing the joints that are tighter than many modern constructions, you're confronted with a humbling reality. These stones have been here for over 500 years. They've outlasted the empire that built them, survived the conquest that destroyed that empire, and endured centuries of earthquakes, weather, and human interference. Spanish buildings built with supposedly superior technology have crumbled and been rebuilt multiple times, while these Incan walls remain essentially unchanged. What knowledge did the Incan master builders possess that we've lost? What insights into materials, forces, and construction did they develop through generations of practice? How did they organize and coordinate thousands of workers to achieve such precision across massive construction sites? These questions remain partially unanswered, keeping Sacsayhuamán in that fascinating space where archaeology, engineering, and mystery intersect. The site serves as a reminder that technological sophistication isn't measured solely by tools and materials, but by what you can accomplish with what you have. The Incas took stone, bronze, rope, and human labor and created architecture that has outlasted steel and concrete structures. They built earthquake-proof walls without understanding seismology as a science because they understood stone, weight, friction, and structural behavior through deep empirical knowledge. Every year, thousands of engineers, archaeologists, and tourists make the pilgrimage to Sacsayhuamán to witness these walls firsthand. Photographs don't capture the experience of standing next to a 200-ton stone and realize it was moved and placed with precision using human power and ingenuity alone. The scale, the craftsmanship, and the sheer improbability of the achievement create a visceral connection to the people who built this. People whose names we don't know, but whose legacy endures in every perfectly fitted stone. Sacsayhuamán stands as testament to human capability, ingenuity, and determination. It proves that ancient people could accomplish extraordinary things that challenge modern assumptions about what's possible with supposedly primitive technology. And it whispers a question that echoes across the centuries. If they could do this, what else were they capable of that we haven't discovered yet?